Welcome to the video for Lecture 29, Section 2. This video covers controller tuning for a steam heat exchanger that is using feed-forward control. We are using the steam heat exchanger simply to give a physical meaning of the problem. Another slow process could be used. The focus is on using feed-forward control and how one tunes the system. Large industrial heat exchangers are generally sluggish. To improve the response, one can add feed-forward control. This slide shows a simple schematic of a steam heat exchanger used to produce hot water. Steam coming in from the top is used to heat the cold water. The steam flow rate is controlled with a flow valve actuator. The hot water temperature is measured and fed back through a flow controller to adjust the steam flow rate. This diagram shows feedback control only. The problem is that the steam temperature fluctuates, which means that the amount of heat input can fluctuate even if the steam flow rate is kept constant. And if the amount of heat input fluctuates, the hot water temperature leaving will fluctuate. The other problem is that the steam heat exchanger is a large process with a large thermal mass, and it will be slow responding. One way to improve the response is to measure the steam temperature and use that information to adjust the steam's flow rate. This would be expected to improve the process response because we don't have to wait a long time for the fluctuating steam temperature to affect the hot water temperature. This slide shows our steam heat exchanger with a temperature sensor in the steam input line. We now have feedback plus feed-forward control. We will use this steam temperature as an input to adjust the steam flow valve. The next few slides are going to describe some of the first-order differential equations that are used to describe the heat exchange going on in the steam heat exchanger. You will not be expected to use them for the course. They are presented as background information and another example of how physical processes are converted into transfer functions and block diagrams. Here is an equation that describes the heat balance and exchange on the water side of the steam heat exchanger. So this equation describes the heat gained by the cold water as it is heated in the steam heat exchanger and becomes hot water. The derivative term on the left side of the equation describes the change in temperature of the water in the heat exchanger with respect to time. The first term on the right-hand side of the equation describes the heat exchange across the heat exchanger with steam on one side and the water on the other side. U describes the heat transfer coefficient of the heat exchanger, and A describes the heat exchanger area. TV is the inlet steam temperature, and T is the outlet water temperature. The next term describes heat gained by the cold water. This term is identical to the one we used to fluid heating problem. Ti is the cold water temperature. Finally, we are going to neglect heat losses to the environment by assuming that the heat exchanger is well insulated around the outside. This is the heat balance and exchange on the steam side of the steam heat exchanger. The derivative term describes the change in temperature of the heat exchanger mass. The second term is the heat exchange across the exchanger surface. This matches the term on the water side, but it is now on the left side of the equal sign. The third term is the heat loss of the steam. This must match the heat gained by the water. It turns out that the relation between steam enthalpy, the H terms in the steam side equation, and the temperature is nonlinear. Hopefully you remember that Laplace transform don't handle nonlinear relations. So we will need to use Taylor series expansion to model the relation between steam enthalpy, H, and the steam temperature, TV. As we did with the water side, to simplify the problem, we are neglecting heat lost to the environment by assuming that the heat exchanger is insulated on the outside, so that the heat lost to the environment can be neglected. This slide lists the solution procedure that must be followed to find the overall transfer function. The details are in the course packet. This slide shows the steam heat exchanger block diagram using feedback control only. This diagram is a bit different than the ones we have seen before because there is a transfer function G3 that describes the heat exchange on the water side, and another transfer function G4 that describes the heat exchange on the steam side. The feedback controller is described by G1, and the steam valve actuator is described by G2. Here are the transfer functions we need for all of the process elements. The controller transfer function is G1 equals Kp times tau is plus 1 over tau is. This expression tells us that we are using proportional plus integral control. We are using a simple gain value Kv for the transfer function for the steam flow valve. We get this assuming that the valve response is linear and the valve time constant is very small relative to the process. We will assume that the gain for the feedback transfer function H1 is 1. G3 describes the water side heat exchange and G4 describes the steam side heat exchange. Their development is in the course packet. Here is the overall transfer function for the steam heat exchanger with feedback control only. Now assume that we are given a plot of the boiler output when the controller is disconnected from the system and we input a small step change in the input of magnitude m equals 1. With the graph, we add the tangent line and we find k, td, and t using the Cohen-Kuhn method for tuning the controller. When we are done, we find that kp is approximately equal to 10 and tau I is equal to 241. More details are in the course packet. Here are two graphs of the time-dependent steam heat exchanger response with feedback control only. The left graph is the servo problem response, and the right graph is the regulator problem response. In both cases, the magnitude of the step change was positive 5 degrees Celsius. For the servo problem, the set point was changed by 5 degrees C, and for the regulator problem, the inlet water temperature was increased by 5 degrees C. And it take over 60 minutes for the response to settle down. So let's see what happens if we add feed-forward control. We are interested in adding feed-forward control because the steam temperature fluctuates. In the earlier sketch, we added a temperature sensor upstream of the steam flow valve. Here is the block diagram for our steam heat exchanger. We add a sensor to the inlet steam temperature line and run the sensor valve through a feedback transfer function named HFF, which supplies a feed-forward control GFF. Here is the new overall transfer function for the steam heat exchanger with the feed-forward elements GFF and HFF. We find this using the concepts from multi-loop block diagram algebra. Here are the two block diagrams. The one without feed-forward is on the top, and the one with feed-forward plus feedback is on the bottom. You can see where the feed-forward elements GFF and HFF are added, and they use the inlet steam temperature to modify the signal to the actuator G2. Here are the two overall transfer functions. The one with feedback control only is on the top, and the one with feedback plus feed-forward is on the bottom. Feed-forward adds the term GFF times HFF times G2 times G3 to the regulator term of the overall transfer function. Feed-forward tuning is beyond what we can cover in this course. It's commonly done using computer simulations, which are followed up with field tests. Feed-forward control also commonly uses a lead-lag transfer function within the feed-forward control element. We have not discussed the lead-lag transfer function so far in this class, so we will simply use a steady-state compensator term, KFF, for GFF. The steady-state gain for the feed-forward controller is given by K4 over KHFF times K2 times K3. Assuming the value is given, we find that the steady-state compensator for the feed-forward controller is equal to -3. Here is a graph with the steam heat exchanger responses for the regulator problem when the inlet water temperature changes by 5 degrees C. The responses are the blue line for feedback-only control and the green line for feedback plus feed-forward control. As expected, adding feed-forward produced a better response. The overshoot is less. Probably with more effort and adding the lead lag transfer function, the feedback plus feed-forward would be even better. This brings us to the end of Lecture 28, Section 2 video. Please write down any questions you have and bring them up in class.